So today we're going to be talking about the product and the quotient rule. But before we get into the rules, let's take a look at what we were doing last week. So if we want to find the derivative with y um, with respect to x, then we said we should FOIL this. So let's go ahead and multiply these two binomials together. So that would be 8x plus 12x squared minus 2x squared minus 3x to the third. And then we could combine like terms a little bit, put it in standard form. And then once we get that all organized, we can find the derivative. So 9x squared plus 20x plus 8 would be the first derivative of y with respect to x. And so the question is, shouldn't there be an easier way? I don't know. I mean, is this really all that difficult? No, but if these were more than just binomial times binomial, if we had larger terms or larger number of terms, I mean, or like exponents out here, squareds and things like that, then there should be some other thing we can do. So our answer here is yes, the product rule. And then just to recap from last week, what about the second derivative and the third derivative? Remember, that's just once you have the first derivative, take the derivative again. So the second derivative is negative 18x plus 20. The third derivative is negative 18. Fourth derivative would be 0, and every derivative after that would be 0. So if we're going to use the product rule, we have to be very careful. And same thing with the quotient rule we're going to talk about on the back. You need to be very organized and neat about your work, liberal use of parentheses, and just general like common sense, think about what's going on here type thing. So you are required to simplify. So what do I mean by simplify? If you have like terms, you should combine them. So combine like terms. No complex fractions. We want to simplify those. So no complex fractions in your final answer. And is there a third thing? Let's see. Combine like terms, complex fractions. I think that might be it. I guess I could say no negative exponents. I don't know if that's going to come up or not. I feel like there was a third bullet point. I'll double check that later. So what is the product rule? If you're trying to take the derivative of two functions that are being multiplied together, if it's not easy to FOIL them out, if you have something more complicated, then the rule is that you have the first function times the derivative of the second. So in this case, f of x times g prime of x plus the second function times derivative of the first. So g of x times f prime of x. It doesn't matter the order in which you write this. So if you like to keep it like f, g, it could be f of x, g prime of x plus f prime times g. I kind of learned it in this order, so this is the way I'm going to show my work. So right now, y is equal to a function x times sine x. I would need the product rule here because I can't simplify this to not have it be the product of two things. So y prime should be the first function x times the derivative of sine x, that's cosine x, plus the second function, sine x, times the derivative of the first function, derivative of x is 1. And then my final answer for y prime would be just simplifying, so x cosine x plus sine x. There's nothing else you can do with that. There are no like terms, so that's the simplified version. For the next one, we have a product to begin, 3 times x cosine x. Now, technically 3x is a product in itself, but constants can kind of come along for the ride. So 3x times cosine x. And then we have to remember we also need to take the derivative of this term, which is just 4 sine x. Okay, so 3x cosine x. The first function is 3x times the derivative of cosine, that's negative sine x, plus, and then it's the second function, cosine x, times the derivative of the first function. Derivative of 3x is 3. And then don't forget about this little 4 sine x, so plus the derivative of 4 sine x is 4 cosine x. And then we'll clean up what we have. We have negative 3x sine x plus 3 cosine x plus 4 cosine x. So we can combine these little cosine x's here. And I'm going to write them first since they're positive and this is negative, but that does not matter. You don't have to do that. I have 7 cosine x minus 3x sine x. All right, so here's the example from our warm-up. Rather than distributing or foiling this together, let's just go ahead and treat it as a first function and a second function. So the derivative of y with respect to x would be the first function, 4x minus x squared, times the derivative of the second function. Derivative of 2 is 0 plus 3, plus the second function, times the derivative of the first function. That would be 4 minus 2x. Distributing is my next step. 12x minus 3x squared, plus, we're going to have to FOIL this together. Instead of plus, I've got 2 times negative 2x is minus 4x. Oh, why did I do that first? I don't know. Plus 8. I guess I could have had plus 8 right there. Plus 12x minus 6x squared. Kind of went out of order there. And then the last step is to simplify. So I'm going to put it in standard form. So I'm seeing negative 9x squared, 12x plus another 12x is 24x, minus 4x is plus 20x, and then plus 8. So that would be my final dy dx. There's no need to try to factor that or simplify it or anything because we're not trying to solve. So once we have dy dx and we can no longer combine like terms, we're good to go. Before we do example 4, there's an extension of the product rule. There are times when you're multiplying more than one function. So for example, if you have 3 functions, the product rule, if you just think about going back to this one, where I said you could just leave this in order, f, g prime, f prime, g, like keep it f, g, f, g. Makes sense to do that here, and each term needs to have a different function with the derivative. So, so you could do it like this. Let's just say we're going to take the derivative of f of x first, multiply that by regular g of x, regular h of x, and then add to that, let's leave f of x normal and take the derivative of g of x, multiply h of x. Finally, we'll leave f of x, g of x normal, and then make it h prime of x. If we had 4 things being multiplied, we'd have to come up with all the different combinations. I don't know that I've ever done a problem where you have 4 things multiplied. That's a bit much. So I don't think we have to worry about that. All right, let's apply that to this. So we have x squared, sine x, cosine x. So let's go with what I wrote down here. So the derivative of x squared is 2x multiplied by the derivative of sine x, which is cosine x, times the derivative of cosine. Oh, what am I saying? Sorry, guys. Got carried away. Derivative of x squared is 2x. I don't want derivatives for the other two. I just want sine x cosine x plus, let's leave x squared the same. Take the derivative of sine x, cosine x, times regular cosine x. And then our last term should be leaving x squared, leaving sine x, taking the derivative of cosine x, which is negative sine x. And then simplifying, let's see, it looks like we have 2x sine x cosine x plus x squared, this would be cosine squared, x, and then minus x squared sine squared x. And again, I know there's a GCF I can factor an x out, but we're not trying to solve anything, so we're not going to bother looking at that. We would just leave it as y prime is equal to this. All right. Before we dive into the quotient rule, we need to remember what we did last week. Not every fraction, from now that we're about to learn the quotient rule, not every fraction requires quotient rule. So remember, if the top is just a constant, like if you're trying to take the derivative of 100 over x, remember, we can rewrite if possible. So let's make a note. Rewrite if, how about this, if easy. Sometimes it's possible to rewrite something, but it wouldn't help you at all. So in this case, I can think of this as 100x to the negative 1. And so the derivative, we'll just call this dy dx. Derivative of that would be negative 100 x to the negative second or over x squared. So we don't need any special rule. That's what we learned last week. And if the bottom is a constant, remember this is just a linear function. There's no need to rewrite anything, but the derivative of that linear function would be 1/17 in this case. And then we had this last week too. If you have a polynomial divided by a single term, a monomial, then remember you can divide that. And if you think of it this way, like dividing x squared over x and 2x over x, it kind of makes this little heart, like giving you the go-ahead that you can do that. So if you divide this out first, you get x plus 2, and then the derivative of x plus 2 is just equal to 1. Now, for examples D and E, I cannot split this fraction up, upside down heart, can't do that. And cosine x over x, there's not really any way to rewrite either of these to get rid of the fraction or be able to just use a power rule or something like that. So these two, if you can't rewrite, this is where we need to use the quotient rule. Quotient rule needed. All right, so what is the quotient rule? If you're trying to memorize this, the little like thing to memorize it, I don't know what to call this, is the trick to memorize it is low D high minus high D low all over low low. So what does that mean? Low is referring to g of x, high is referring to f of x. So low D high, so the bottom function times the derivative of the top function minus high D low. So when we say D high, D low, derivative of low. So high, f of x, times derivative of the low function, g of x, g prime of x, all over low low, so all over g of x squared. Low d high minus high d low over low low. Okay, let's put that into practice. Our low function is x squared plus 5. Our high function is 3x minus 4. Low d high. So low is the bottom part, x squared plus 5. D high is the derivative of 3x minus 4. Minus high d low, the top function, times derivative of x squared plus 5, all over low low. We almost never square this out. Same rule that we had with just simplifying rational functions. We don't usually mess with the denominator because there are some times where it might cancel out, or if we're trying to like find critical numbers and things, we might need that to be in its factored form. All right, so we're not finished. We don't leave it like this. We still need to simplify. So I'm going to, since I'm kind of out of room, I'm going to distribute just up above here. So 3x squared plus 15. Think of this as a negative 2x that you're distributing through here. Negative 2x times 3x is minus 6x squared. Negative 2x times negative 4 is plus 8x. And then I'm going to combine like terms here. So negative 3x squared plus 8x plus 15. Now, back in pre-calc and in math 3, we said, like, how do I know when to stop? Should I be trying to factor this? And, like, this one might have some possibilities, and I don't know if it factors or not off the top of my head, but do I need to waste time on a test trying to factor this thing? And that answer is no, because you can quickly look and see if it's negative 3x squared, is there any way that the factor is going to be x squared plus 5? So that's a no, because this would need to be negative 3x to the fourth. And so the only reason to factor the numerator is to try to cancel a factor in the denominator. And I can already see that that's not going to be a possibility. So do not waste time trying to factor rational expressions when you really don't need to. Okay, our next one, low D high. Low D high minus high D low. Let's go over that again. Low sine x, derivative of 5x is 5, minus high 5x d low, derivative of sine is cosine, over low sine squared x. Simplify, we like coefficients to be out in front, so 5 sine x minus 5x cosine x over sine squared x. I see that I can factor a 5 out, but again, it's not going to help me cancel. The only thing you have to be kind of mindful of is if you're working on a multiple choice problem and you don't see your exact answer in the choices, remember one of the answers might be your answer but factored, or like if they swapped out for some reason a 1 minus cosine squared for a sine squared, something like that. So we just have to be on the lookout. Before I jump into the quotient rule for this one, I have a complex fraction, so let's work on it a little bit by getting rid of the complex fraction before we dive right into the quotient rule. So you should always simplify if you can. If I multiply by x over x, I get 3x minus 1 over, now here I am going to do x squared plus 5x. If I left it as x times x plus 5, then when I do the derivative of the low function, I'd have to do a product rule, and that seems pretty unnecessary. So remember, if it's easy, distribute through. All right, so here's my function. Low d high minus high d low, 2x plus 5, over low, so x squared plus 5x squared. And then we can work on this. So let's see, 3x squared plus 15x. Be careful when you're subtracting the product of two binomials. I think it's a good idea to take this to one more step and write minus and set up parentheses for what you're going to get when you FOIL this, rather than trying to change the signs in your head. So what I mean by that is it's minus the quantity, 6x squared, plus 15 minus 2 is plus 13x minus 5, all over, same thing down here, squared. And then let's see, I'll just change signs up above. So minus 6x squared minus 13x plus 5. So negative 3x squared. 15x minus 13x is plus 2x. And then we said we have plus 5. And again, maybe that factors, maybe it doesn't, but I don't want to waste any time thinking about it because I know it's not going to factor into x squared plus 5x. So I'm not going to worry about that because x squared plus 5x needs to be squared. And yeah, so anyway, why do we have to simplify all these things? Like, why can't we just leave our answer in terms of the product rule here? One answer is it just looks nicer, right? A on the right side is much nicer to work with than A on the left side. But also, most of our time this semester will be spent trying to set f prime of x equal to 0 and solve. And in order to do that, if you set this left side equal to 0, you're going to have to do all the work to get it to look like the right side and then be able to actually solve the thing if you're doing your algebra correctly. So why simplify? Because we're going to be solving. Usually when f prime x is equal to 0, but also just some other things too. So you just should definitely simplify every time. There are some trig derivatives. We're going to derive, if you forget on test day what the derivative of tangent is, for example, you can do it really quickly, but also it would be best to memorize these. You're going to see some patterns and some things that you can work with, so you don't want to waste time always having to derive it if you can remember some of these. Remember, the ones we know already are the derivative of sine x with respect to x is cosine x, and the derivative of cosine x with respect to x is equal to negative sine x. So remember that we already learned these two. So those should definitely be memorized. The derivative of tangent x, well, remember tangent can be rewritten as sine x over cosine x. So really, we're saying, what's the derivative with respect to x of this rational function? And we can use our quotient rule for that. So low d high minus high d low all over low low. That becomes cosine squared x plus sine squared x over cosine squared x. We have to think about our trig identities. Remember last year, cosine squared plus sine squared is equal to 1. And the reciprocal of cosine squared, the reciprocal of cosine is secant, so this should be secant squared x. So you want to memorize that the derivative of tangent x is equal to secant squared x. I kind of remember that one because remember we have a trig identity that says tangent squared plus 1 is secant squared. Excuse me. So I kind of remember that those go together. All right, let's do derivative of secant. Is it just going to be tangent squared? We can check on that. Secant is 1 over cosine x. So I'm still going to use quotient rule on this. Low derivative of 1 is 0, low d high, minus high d low, all over low low. This is 0. This is plus sine x. So sine x over cosine squared x. If it helps, let's write cosine squared x expanded out like that. Sine over cosine is tangent x. And 1 over cosine is secant x. So the derivative of secant x is not just tangent squared x, it's tangent x secant x. Again, just something to memorize. Derivative of cotangent x. So cotangent is cosine over sine. Low d high minus high d low all over low low sine squared x. Negative sine squared x minus cosine squared x all over sine squared x. Negative sine squared x minus cosine x, that's just distributing a negative through the Pythagorean identity we know, cosine squared plus sine squared. So that is negative 1 over sine squared x. And so that's equal to negative cosecant squared x. I do have, so if I know that the derivative of tangent x is equal to secant squared x, I kind of remember it as just put a co in front of both of those. The derivative of cotangent x is equal to negative cosecant squared x. So we'll talk about the negative in a minute, but you can kind of remember those that way. Next one. Okay, cosecant is 1 over sine x. So low d high minus high d low all over low 0 minus, so this is negative cosine x. Let's do the same trick we did in the previous blue one. So expand out sine x and sine x so you can see this more clearly. Negative cosine x over sine x is negative cotangent x, and then 1 over sine x is cosecant x. And that same put a co in front of it trick kind of works. If you can remember that the derivative of secant is tangent secant, then the derivative of cosecant is cotangent cosecant, and you have to remember that it's negative. There is a trick to remembering that it's negative. Take a look at the derivative of cosine. Take a look at the derivative of cotangent and the derivative of cosecant. Those derivatives all have negative signs in them. So, taking the derivative of any trig function that starts with a c, cosine, cotangent, cosecant, its derivative needs to have a negative symbol in it. So that's a quick way to remember that. The derivative of cosine is negative, derivative of cotangent is negative, derivative of cosecant is negative, and then the other ones are positive. So there are lots of little tricks to remember, but you do just need to memorize all 6 of our trig derivatives. Okay, so using those shortcuts now, we're not going to derive for tangent, secant, or any of this. We're going to assume that we know this. So the derivative, let's see, dy dx. I'm sorry, it's not dy dx. Oh, I'm glad I wrote it like that. dy d theta. Remember, it matters for your notation here. I was going to write dy dx, but the variable is not x. It's the derivative with respect to theta. So I almost said y prime, but it's good to write it like this. The derivative of theta is 1. And we said the derivative of tangent is secant squared. So 1 minus secant squared theta. Now with these trig ones, how far do I have to take it? Is this one of those identities? Remember we said tangent squared theta plus 1 is secant squared theta? That's one that you really should have this one. You should have the Pythagorean identities memorized as you're going through this BC course this year. So let's see. If I subtract secant squared over, it means I would have had to subtract tangent squared to the other side. So yeah, 1 minus secant squared is equal to negative tangent squared. How do I know when to stop on a free response question? On a free response, you can stop here, 1 minus secant squared theta. On a multiple choice, if you don't find that answer, remember, you need to remember that your answer might be in there, just using trig identities, it might be rewritten. So you just have to be on the lookout for that. X secant x. This is a product rule, so be careful. We have to use our product rule here because there's no way to get rid of this x multiplication out in front. So it's the first function times the derivative of the second. The derivative of secant was tangent secant or secant tangent, whatever. We wrote it as tangent x secant x, so I'll do that. So first function, derivative of the second, plus second function times derivative of the first. So x tangent x secant x plus secant x. I could stop there on a free response, or maybe I'm looking for my answer in a multiple choice, so I factor out a secant x. X tangent x plus 1. Remember, tangent x plus 1 is not anything that's not equal to secant, so that's as far as it could go. And your answer could be in this form or in the previous form. All right, for my next one, I have a couple of options here. I can divide, which is probably what I would first think to do. 1 over sine x is cosecant x minus cosine x over sine x is cotangent x. And then I can take the derivative of each term. So the derivative of cosecant is cotangent negative cotangent x cosecant x. The derivative of cotangent is negative, so this minus is going to turn into a plus cosecant squared x. And again, I could factor out a cosecant x, and I'd probably rearrange my terms if I did that. Taking it out of cosecant squared, I get cosecant x and then minus cotangent x. I would stop there. I could maybe keep going. What was the other option? Sometimes it's helpful to, like if this would have been more than one term with the sine x, it might have been helpful to multiply by the conjugate of 1 minus cosine x. Like it might have been useful to multiply by 1 plus cosine x over itself. This is something we did in our trig identity days. That would give me 1 minus cosine squared x, and then remember, you don't usually multiply in the denominator. 1 minus cosine squared x is negative sine squared x. And that gets it into negative sine x over 1 plus cosine x. That did not help me in terms of making life easier, but like this is a route you could take, and then you'd have to use quotient rule. So definitely not the path of least resistance. But again, it's a nice trick to know, because if this had this have been like 1 plus sine x, then I wouldn't have been able to just divide out if I didn't have a single term, and I'd have to do some sort of work like this to try to get somewhere else with it. So if I take the derivative of this, I should get something close to or the equivalent of this. Not when I say close to, I mean it might not be in terms of cotangents and cosecants. It'll be in terms of sines and cosines, and I'd have to work on it further to get to this point. All right, that should be it for today's notes. Come back tomorrow for a little bit of chain rule.